All right, welcome to Crypto Miner CHR, consultations, hosting, and repair. And today we're going to go over the L3 hashboard repair guide here. Let me go ahead and open it up for you. This is a 10-page little booklet. The contents of this booklet mainly tells about L3 Plus, how to use the test box to accurately locate the various faults of the computing board. Scope, applicable to all L3 Plus production after-sales outsourcing maintenance site. Maintenance platform requirements. Constant temperature soldering iron, 350 degrees to 400 degree, which is in Celsius. The tip soldering iron tip is used for soldering small patches such as chip resistors and capacitors. The hot air cylinder is used for chip disassembly and welding. Be careful not to heat it for too long of a time to avoid PCB blistering. APW3 power supply, output 12 volt, 133 amp max. It is used to test and measure the computing board. Number 4, you need a multimeter. Photo shoot L3 Plus text fixture. Conditionally configurable oscilloscope. 5, flux, washing water, and absolute alcohol. Washing water is used to clean up the flux residue and appearance after repair. Plant tin fixture, plant tin steel mesh, solder paste. When replacing a new chip, the chip must be tinned. Thermal conductive glue, black. 3461, used to reattach the heatsink after repair. All right, 2, operational requirements. 1, maintenance personnel must have certain electronic knowledge, more than 1 year of maintenance experience, proficient in QFN package soldering technology. After repairing, the computing board must be tested for more than 2 times and it is okay, can pass. Pay attention to the operation method when replacing the chip. After replacing any parts, the PCB board has no obvious deformation. Check the replacement parts and the surrounding parts for open circuit and short circuit problems. Determine the maintenance station object and the corresponding test software parameters and test fixtures. Inspection tools, whether the fixture can work normally. Principle and structure. 1. L3 Plus by 12 series of voltage domains. Each voltage domain has 6 pieces. BM 1485 chip. Shared by all boards. 72 pieces. BM 1485 chip. 2. BM 1485. The chip has a built-in buck diode. The function of the step-down diode is determined by the specified pin of the chip. L3 Plus clock is 25 M signal crystal in series from the first one chip to the last chip. L3 Plus independent small heat sink on the back of each chip. The small heat sink on the back is fixed on the back of the IC with the thermal glue after the initial test of the board. After the repair and replacement chip has passed the test, you need to eventually coat the IC surface. Apply black thermal conductive glue and heat to fix it. Key point analysis. 1. The following figure is a schematic diagram of the signal trend of the L3 Plus signal board. Signal trend. This is figure 1. So as you can see, this is the L3 Plus version 1.0. It is a little bit different on the other boards, but it's just basically the numbering is a little different. So as you can see, it starts at chip 1, and you have the first domain goes to chip 6. So you have 6 chips. And then you go across all the different domains. You have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 domains, just like we just talked about. And it starts from chip 1 to 6, 7 to 12, so on and so forth to 67 to 72. Okay. Sequential transmission. In standby and operation, the voltage is 0.9 volts. No, chips are transmitted sequentially, not inserted I/O. The line voltage is 0. The voltage during operation is 1.8 volt. Mouth 12 feet back to the control board. Not plugged in I/O, the signal voltage is 1.8 volt. The voltage is also 1.8 volt. In standby, 0. When calculating, 0.3 pulse signal around. Loose I/O signal and standby 0 volt. When calculating, 1.8 volt. When repairing, the test point between the test chips is the straightest. The fault location method of the connection. L3 plus operation board test points are arranged is RST, BO, RI, sometimes it's RX, CO, or sometimes TX, and clock signal, CLK. Now, if you notice on the L3 boards, they actually tell you which chip you're working on just by looking at those numbers there next to each test points. So now we scroll down. This is going to tell us exactly what we're looking at here is the actual hash board itself. And so you have the 14 volt, and that's where your boost circuit is. Then you have your DC-DC circuit right here in the center. Then over on the top right is your I/O, and that's what goes to your data cable that goes out to your control board. Now down at the bottom, you'll see what they were talking about. There should be 18 volts, 1.8 volts running through there. There should be 0.9 volts on the LDO. 25M. And then right there in Chinese is actually saying your test points. Okay, now let's read this. Figure 3, key circuits on the front of L3 plus arithmetic board. 2, voltage domain. The whole board has 12 voltage domains. Each voltage has 6 chips. In the same voltage domain, each chip is powered in parallel and then connected in series with other voltage domains after paralleling. The circuit structure is as shown below. 4 shown. I don't know if we can kind of zoom in here and actually see this better. Still pretty blurry. So this shows you the different circuit of each chip and how they go out and where they're supposed to be attached to. You have the different resistors and the different capacitors. You can see where they're grounded at. That's why it's recommended that you know at least a little bit of electronics to be able to know what you're dealing with here. Go back. Okay. Now we're going on to page 4. See, it actually kind of zooms in for us, so we actually didn't have to take a look at that. Principal analysis of voltage domain single chip, as shown below. 5. Figure 6. Figure 5. BM1485 circuit diagram. So this is a single chip. Shows you exactly how it goes. So you have your little test points in the top right there. As you can see, they each go in, and it goes into leg 1, 2, 3, 4, and 5. 6, 7, 8, nothing. 9, 10, 11, 12, all the way to 14. And that gets grounded, which is pin 30. Take a look, it tells you all the different capacitance and everything that you need for all your different resistors and everything here. There you go, it shows you exactly what the chip looks like. You have a big flat ground area and a VDD area. Oh yeah. Okay. The above is the function of each pin of BM1485 chip. During maintenance, the main test points are 10 test points before and after the chip, 5 before and after the chip, clock, CO, RI, BO, RST. Core voltage, LDO 1.8 volt, PLL 0.9 volt, DC DC output, and boost 14 volt voltage. Detection method. When the I/O line is not plugged in and only 12 volt is plugged in, the DC-DC output is about 10 volt, and the boost output is about 14 volt. The test point must have clock 0.9 volt, RI 1.8 volt voltage, which his test voltages are all 0. When the I/O line is plugged in and the test button is not pressed, when the I/O line is plugged in and the test button is not pressed, neither DC to DC nor boost has voltage output. After pressing the fixture test button, the PIC starts to work. At this time, the DC to DC output fixture test, the voltage is set by the program, and the boost will work with it. Then the tool outputs work and returns nonce after calculation. At this time, the normal voltage of each test point should be clock 0.9 volt. voltage is set by the program, and the boost will work with it. The tool outputs work and returns nons after calculation. At this time, the normal voltage of each test point should be clock 0.9 volts, co 1.6 to 1.8 volts. When the tool is sending work, the DC level will be pulled down because the co is negative, and the instantaneous voltage is about 1.5 volt. Ri should be 1.6 to 1.8 volt during calculation. The abnormal or low voltage will cause the calculation board to be abnormal, or the computing power is zero. BO, it is 0 volt when there is no operation, and there will be a pulse jump between 0.1 and 0.3 volt during operation. RST is 1.8 volts. Each time you press the test button on the tool, the reset signal will be output again. When the above-mentioned test point status and voltage are abnormal, please estimate the fault point based on the circuit board. Please estimate the fault point based on the circuit before and after the test point. Visible from the above list. Clock signal. By the chip, 23 foot in, 5, when the pin is connected across the voltage domain. The 5, the pin, is connected to the next chip through a 100 NF capacitor, 23 foot. TX signal. By the chip 25 foot in, 4 foot out. RX signal by the chip 3 feet return, 26 pin out. BO signal by the chip 27 foot in, 2 pin out. Reset signal by the chip 28 foot in, 1 pin out. Test the signal voltage of each chip. Core voltage, LDO, 1.8 OV. PLL, 0.9 volt, and other voltages. Core, 0.8 volt. When this voltage is abnormal, it is generally the core of the chip in the voltage domain is short-circuited. So that's really good to know right there. So when the core is 0.8 volt, when this voltage is abnormal, it is generally the core of the chip in the voltage domain is short-circuited. LDO, 1.80, 1.8 volt. When the voltage is abnormal, the chip LDO 1.80 is short-circuited or open. PLL 0.9, 0.8 volt. When the voltage is abnormal, the PLL-09V power supply of a certain chip in its voltage domain is short-circuited. Judging the operating status of the computing board, the computing capability of the chip, and the temperature sensitivity based on the information in the printing window of the manufacturing tool. 3. I/O port. I/O is composed of 2x9 pitch 2.0 PHSD 90 degree in line double row. The pin definitions are shown in figures 8 below. Figure 8, pin definition of I/O port. So we have 1 ground, 2 ground, 3 SDA, 4 SCL, 5 plug 0, 6 A2, 7 A1. Sorry, can't take a call right now. Where were we? 6A2, 7A1, 8A0. 9 is ground 1. 10 is also ground. 11 TXD, 12 RXD, 13 ground, 14 ground, 15 RST, 16 D3V3. And you can see that go out. And then 17, 18 are nothing. So, as shown in the figure, 1, 2, 9, 10, 13, 14 feet, it is ground, as we just said. Now, 3, 4 feet, SDA, SCL, it is the I2C bus of DC to DC PIC, which connects the communication between the board and the PIC. The control board can read and write the PIC through it. Data to the control the operating status of its computing board. 5 feet, plug 0. It is the identification signal of the arithmetic board. This signal is pulled from the arithmetic board by a 10K resistor to 3.3 volts. So when the I/O signal is plugged in, this pin should, apologize, some of this guide is cut off. It is high level. Let's try to understand what's missing there. All right, let's continue. 6, 7, 8 pins. A2, A1, and A0 PIC address signal. 11, 12 feet, TXD, RXD. It is the channel of computing power at the 3.3 end of the arithmetic board, which becomes TX, or CO, and RX, RI, signals after being divided by resistors. The I/O port pin terminal level is 3.3 volts. After dividing the voltage through the resistor, it becomes 1.8 volts. Now, 15 feet is RST. It is the 3.3 volt end of the reset signal, which becomes 1.8 volt reset signal after being divided by resistors. 16 feet, D3V3, supply the 3.3 volt power supply for the computing board. The 3.3 volt is provided by the control board, mainly to provide the working voltage for the PIC. So that's what the D3D3 is for here at the pin 16, or feet. All right, we have another diagram here. It shows you exactly how those pins go out. See, 1, 2 is ground. And this is J1 on your board here. Got the different resistors shows where they go out. So plug 0 goes out through a resistor, 10K, comes out D3, V3. We have reset goes in, and it has 2 resistors, and it goes out to ground as well as more down the line of reset. Got another one as well. TXD, TXN. All right. TXN voltage is 1.8 volts. Reset in voltage is also 1.8 volt. 4. 14-volt boost circuit. Responsible for boosting DC to DC, 10 dash, so it's between 10 and 10.4 volt, to 14 volt. The principle is to boost 10 volt to 14 voltage through U111 RT8537 switching power supply. C1072 is charged and discharged to obtain 14 volt of the positive electrode of C1072, as shown in figure 11 and figure 12. So now figure 11 shows you the circuit diagram, and figure 12 actually shows you it on the PCB board. So we have figure 11, 14-volt boost principle diagram. So as you can see the diode, you can see the capacitors and everything. You also see the L1 there. Note, the abnormal increase in the voltage of the boost circuit can easily cause damage to the LDOs in the last 4 voltage domains of the operation board, as well as damage the chip. The abnormal boost voltage is most likely caused by the oxidation of U111, R996, and R997. Boost circuit voltage output test points are both ends of C1072. So to test the voltage of the output of the boost circuit, you want to test both ends of C1072. DC PIC consists of PIC 16L F1704. As shown in figure 13 and figure 14, the device that stores the frequency information and voltage value of the arithmetic board chip can also be used to control the DC to DC output voltage of the arithmetic board. Go ahead and let you take a look to study this real quickly. This is the PIC chip. Looks like it's right next to the DC to DC circuit, directly to the right. When PIC is working, it needs to control and send a heartbeat signal every minute. With heartbeat information, PIC will work for 1 minute and then shut down. PIC pin 1 is VDD, 3.3 volts. 14 is ground. Pins 9 and 10 are the 12C bus and Pins 9 and 10 are the 12C bus that connects the I/O port to the control board. Pins 5, 6, and 7 are the PIC address. Pin 4 is PIC 3.3 volt. Pin 8 is the FB out. Pin 8 is the FB input of PIC output to control the DC-DC voltage. Pin 11 is the EN signal output by the PIC, which controls the DC-DC working status. So figure 13 is the PIC schematic diagram. Shows you the different resistors here, which is ground, and we just discussed what each one of those pins does. And then figure 14 is the PIC power road. 6, DC-DC circuit. It is composed of LM27402SQ and CMOS CMOS tube. TPHR 9003 NL, as shown in figure 15 and figure 16 below. Now you get to see the actual schematic diagram with figure 15 of the DC-DC schematic. DC-DC output voltage test point is both ends of capacitor C948. Now this is for, like I was saying, version 1.0. But this here, I have one of the later models, version 1.61, and that is C1221. When the DC-DC voltage is abnormal, first check whether the PIC voltage value is the same as the DC-DC output voltage through the printed information of the tool. If not, please replace the small capacitor around the LM27402SQ first. So that could be a major fault there. If there is no DC to DC output, please check the EN voltage of R13 and R14 is about 1 volt. R11 voltage is 12 volts. Whether the PIC works abnormally and whether the PIC can normally receive the 12C signal of the control board. 8. 1.8 volt. LDO is composed of 1.8 VLDO SPX 5205 M5 underscore L underscore 1 underscore 8. As shown below, SPX 5205 M5 pins 1 and 3 are input, and pin 5 is 1.8 volt output. The PL 0.9 volt voltage is obtained by dividing the voltage of LOD 1.8 through 2 resistors. As you can see here, the two resistors. Temperature sensing circuit. It is composed of sensor IC. The temperature sensor chip collects the built-in temperature sensor of BM1485 through pin 6.7 of BM1485. After the temperature sensor parameter is collected, it finally passes through pins 15 and 16 of BM1485 and returns to FPGA of the control board from RI. The principle is shown in figure 21. So here it is, the figure 21 schematic diagram of temperature sensing. And as we just found out with the L3 boards, it is sensed from a sensor within the actual chip itself. We're talking a hash chip. Now, routine maintenance process, reference tips or steps. Observe the appearance, measure impedance, measuring voltage, and system tools test. Detect each test point, voltage and power supply. According to the detection information, locate the fault. Positioning to the chip, first welding, re-welding, invalid replacement. Test more than twice, okay, can be considered repaired. Troubleshoot, type record. Okay related aging. Routine testing. First of all, visually inspect the computing board to be repaired and observe whether there is any displacement, deformation, or scorching of the small heat sinks. If any, it must be processed first. If the small heat sink is displaced, first after dismantling, wash off the original glue and readhesive after the repair is passed. Secondly, after the visual inspection is no problem, the impedance of each voltage domain can be tested first to detect whether there is a short circuit or an open circuit. If found, it must be dealt with first. Again, check whether the voltage of each voltage domain has reached 0.8 volts. The voltage difference of each voltage domain shall not exceed 0.05 volts. If the voltage of the certain voltage domain is too high or too low, the circuits in the adjacent voltage domain generally have abnormal phenomena. Need to investigate the reason first. So basically, you want to test each chip, and if it's not passing with the proper voltage, it's got to be somewhere else. After the routine test is not normal, number 2, after the routine test is no problem, the short circuit test of the general routine test is necessary, so as not to burn the chip or other materials due to the short circuit when the power is turned on. The test box can be used for the chip test, and according to the result of the test box is judged and positioned. 3. According to the display results of the test box detection, starting from the vicinity of the fault chip and detect the chip test points, clock in out, TX in out, RX in out, B in out, RST in out, and VDD. VDD 0 V8, VDD 1 V8 equal voltage. Then, according to the signal flow, except the RX signal, the reverse transmission 72 to 1 chip. Several of the signals, clock, co, bow, RST, are forward transmission, 1 to 72, and the abnormal fault is found through the power supply sequence point. When locating the faulty chip, the chip needs to be welded again. The method is to add flux around the chip, preferably no clean flux. Heat the solder joints of the chip pins to a dissolved state, and then gently move down and left to press the chip, to prompt the chip pins and pads to re-engage and close the tin in order to achieve the effect of tinning again. If the fault remains the same after resoldering, you can directly replace the chip. So basically, don't just take the chip off. You want to see if you can reset or reseat the chip, and then if it's still not working, go ahead and replace it. 6. After repairing the arithmetic board, the test box must be inspected twice or more. 2 test times before and after. The first time, after the replacement of parts is completed. The calculation board needs to be cooled down and then pass the test after. Interesting. Might have to rewrite this guide because it's not, good grammar, but okay. Let's try it again. After repairing the arithmetic board, the test box must be inspected twice or more. 2 test times before and after. The first time, after the replacement of parts is completed. The calculation board needs to be cooled down and then pass the test. After passing, put it aside. For the second time, after a few minutes, wait for the arithmetic board to cool down. Test again. Although the time for the 2 tests is a few minutes, this does not affect the work. Put the repaired board aside. Continue to repair the second board. Wait for the second board to be repaired and set it aside to cool down, and then test the first board. In this way, the time is just staggered, and the total time is not delayed. The repaired board, it is now on 7, the repaired board, it is necessary to classify the faults and make records of the type, location, reason, etc. of the replacement components. To prepare for feedback back to production, after sales, and R&D. 8. After recording, install it into a complete machine for formal aging. 5 failure types. Common fault types are: 1. The impedance of each voltage domain is unbalanced. When the impedance of some voltage domains deviates from the normal value, it indicates that there are parts in the abnormal voltage domain that have open circuits and short circuits. The most likely to be caused by the something big, but there are 3 chips in the voltage domain, and often only one has a problem when it fails. The method of finding out the problem chip can detect and compare the abnormal point through the test point to ground impedance of each chip. If you encounter a short circuit phenomenon, you can remove the heatsink. Oh, sorry, let me fix this. Be right back. All right, looks like we're back. So, 5 failure types. Common fault types are: 1. The impedance of each voltage domain is unbalanced. We already read most of this. If you encountered a short circuit phenomenon, you can remove the heat sink on the chip with the same voltage first. and then observe when the chip pins are connected to the solder. If the short circuit point cannot be found in appearance, the short circuit point can be found according to the resistance method or the current interception method. 2. Voltage unbalance in voltage domain. When the voltage of some voltage domains is too high or too low, it is generally due to the existence of abnormal voltage domains or adjacent voltage domains, I.O. The abnormal signal condition leads to abnormal working status of the next voltage domain and voltage imbalance. Only by detecting the signal and voltage of each test point, the abnormal point can be found. Individually, it is necessary to find out the abnormal point by comparing the impedance of each test point. Pay special attention. Clock signal and reset signal. These two abnormalities are most likely to cause voltage imbalance. 3. Lack of chips. The lack of a chip means that the test box cannot detect all of them during the test, 72 for each chip. It is often impossible to detect as many chips as they actually are, and the actual missing undetectable, the abnormal chip is not there display at this time. It is necessary to accurately locate the abnormal chip through testing. Positioning method can be used. TX cut off the distribution method. Find the location of the abnormal chip is to convert a certain chip TX signal to ground. For example, connect the first 50 chip TX after outputting the ground of the voltage domain. In theory, if all the chips in front are normal, the test box should display the detection 50 chips. If not detected 50 chips, indicating that the abnormality is in the 50 chip before. If detected 50 chips, indicating that the abnormal chip is in the 50 after a chip. By analogy, use dichotomy to find the location of the abnormal chip. Broken link. The broken link, this is number 4. The broken link is similar to the lack of a chip. But the broken link does not mean that the chips that cannot be found are abnormal. But because a certain chip is abnormal, all the chips behind the abnormal chip fail. For example, a chip itself can work, but it will not forward other chip information. At this time, the entire signal chain will abruptly stop here. Losing a large part of it is a broken link. Generally, the broken link can be displayed in the text box. For example, when the test box detects the chip, it only detects 14. If the preset number of chips is not detected in the test box, it will not run. So only how many chips are detected will be displayed. 14. In the 14 check the voltage and impedance of each test point before and after each chip to find the problem. Does not run. This is number 5. Not running means that the test box cannot detect the chip information of the control board, and it displays no hashboard. This phenomena is the most common and involves a wide range of faults. Number 1. Non-operation caused by abnormal voltage in a certain voltage domain. The problem can be found by measuring the voltage of each voltage domain. 2. Caused by a chip abnormality. The abnormality can be found by measuring the signal of each test point. Clock signal, 0.9 volts. The signal is made by one chip, one number chip output to 72 number chip. But the current version has only one crystal oscillator. But the current version has only one crystal oscillator as long as there is an abnormal signal LCK, yes. All the following signals will be abnormal. Search in order according to the signal transmission direction. TX signal 1.8 volts. This signal is caused by 101 all the way to chip number 72. When a certain point of the dichotomy is abnormal, it can be detected forward. RX signal 1.8 volts. This signal is caused by 72 through 1 if the number returns. Confirm the cause of the fault through the chip signal trend. And the S17 and S9 arithmetic boards are not running, this signal is the highest priority, and searching for this signal is the priority. BO signal 0 volt. The letter number is detected on the chip RI when the return signal is normal. It can be pulled high, otherwise it is low. RST signal 1.8 volt. Power on and plug in the computing board I/O. After the signal will change from 0, 0 to the directions of and 72 are transmitted to the last chip. A certain chip, VDD cause, number 3. It can be measured whether the potential difference of each voltage domain is normal. In general, when VDD, the voltage is 0.8 volts, when the normal voltage of each test point in other voltage domains is also 0.8 volts. In order to ensure that each electricity balance between pressure domains. Number 4. Of a certain chip, VDD 1V8 abnormal voltage. Determine a certain value by measuring the test points of each voltage VDD 1V8 whether the voltage is normal. Under normal circumstances, I/O voltage determines the voltage of each test point. When I/O, the voltage is 1.8 volts. When the test points in other voltage domains are pressure is also 1.8 volts. Step down circuit and caused by abnormal boost circuit. Number 5. Can directly measure the upper left corner of the computing board. C948 capacitor output is the voltage at both ends, 10 to 10.4 volts between. No one more than the need to re-upgrade U3 PIC. After confirming that the PIC voltage is normal, check measurement U111. Is there an output 14 volt voltage? Not detected peripheral parts and U111 itself. 6. Low computing power. Low computing power can be divided into 2 parts. 1. When the test box is tested, the box receives nonce insufficient. It shows because of insufficient computing power and G. This phenomenon can be seen directly through the serial port printed information on the test box to see the return of each chip. Nonce judge the quantity. Generally return nonce if the number of chips is lower than the set value. Troubleshooting should be carried out and the chip can be replaced directly except for non-faulty soldering and peripheral causes. 2. When the test box was tested, the computing power was low after the whole machine was installed. Most of this situation is related to the heat dissipation conditions of the chip. Special attention should be paid to the glue used for the small heat sinks of each chip and the ventilation performance of the whole machine. Another reason is the voltage of a certain chip is critical. After the whole machine is installed, 12-volt, the difference between the power supply and the power supply during the test results in a deviation between the test hash rate and the running hash rate. You can use the test box to test after turning it down and adjust the voltage slightly. DC adjustable power supply, 12 volt after the output. Test again to, and then it's cut off. Make sure everything is working properly. 7. A chip NG refers to the test box serial port information showing the return of a certain chip when it passes the test box test nonce, insufficient, or 0. The chip can be directly replaced in addition to eliminating the problem of virtual soldering and peripheral components. Maintenance. During maintenance, the maintenance personnel must be familiar with the function and flow direction of each test point, the normal voltage value, and the ground impedance value. 2. Must be familiar with chip soldering so as not to cause PCB blistering and deformation or pin damage. 3. BM1485 chip package, 14 pin on both sides of the chip. The polarity and coordinates must be aligned during welding, and they must not be misaligned. 4. When replacing the chip, the thermally conductive fixing glue around the chip must be cleaned to prevent the IC from hanging in the air or poor heat dissipation during soldering, which may cause secondary damage to the chip. End of the guide. I hope you enjoyed. Make sure to subscribe, hit the thumbs up, and tune in for more.